Okay, today we are going to talk about sampling distributions for means. Everything that we do today is going to be very similar to what we did with our proportions. The only difference is we're going to be dealing with means, and standard deviation is calculated a little bit differently just because you have to think of the fact that we are taking a mean of an entire sample size. So I'm going to kind of go through the first couple of things. Most of this is going to look like proportions. So sampling distribution of X bar, remember X bar is going to represent sample means, is very much like the sampling distribution of P hat, our sample proportions. So what is the histogram going to look like? Well, the center is going to be at the true mean mu. Very, very similar to proportions. Spread is calculated a little bit differently. It's going to be based on the true standard deviation and the sample size. So they will give you a standard deviation value. However, it's not what you will use directly for calculating a probability. You have to do a little bit to it. You have to use sample size to get the correct value. And again, as the sample size gets larger, the standard deviation is going to get smaller. And the shape of the histogram, again, will be unimodal and symmetric. We want it to look like a normal model because when it's a normal model, we're able to say all of these rules that we've talked about when we come to normal distributions. We can calculate probabilities. We can use the 68, 95, 99.7 rule. We can use z-scores in our z-tables. All of that is good to go once you can assume it's approximately normal. The way we do that is we check conditions. So what's nice about this is it shares two conditions with our sample proportions. So it shares the randomization and the 10% condition. Random, you want to make sure your sample was selected randomly. And 10% condition is you just want to make sure your sample size is no larger than 10% of the population. Remember, when we get over 10%, we tend to introduce bias into our sample, and that is what we want to avoid above all things. Is we want to make sure our sample is representative and not biased towards one group over another. The third thing is different. We do want to check if it's approximately normal. However, we do not use the success fail condition for means. Instead, you have some options. Generally, the first thing you are going to check is the central limit theorem. And that just means when my sample size is large, no matter what the original distribution looks like, no matter what the population looks like, it's going to start to look normal. It's going to, as I get more and more samples, it's going to look normal, centered around the true mean. And typically, the minimum amount of sample experimental units you want is 30. So we always check, is our sample size bigger than 30? If it is, we can say the central limit theorem applies, therefore it's approximately normal. If you do not have a sample size that large, you do have other options. Sometimes you are given a graphical representation, a histogram, a box plot, a dot plot, something that has the data organized. And if you can see normality in that graph, it's a good to go. You can say, based on the given graph, we'll assume it's approximately normal. Now, sometimes, and I will say most likely not on the AP exam, they will give you data for you to enter into your calculator and see for yourself, is it approximately normal? The reason why I say this most likely will not happen on the AP exam is because they understand that calculator error happens, and the possibility of you striking the wrong number is very, very high. So for the most part, they will give you a graphical representation if that's the direction they want you to go. Third thing, sometimes it just tells you. Sometimes in the problem, it'll say assume an approximately normal distribution or assume normality in the distribution. If that's the case, you will just say something similar to what we do for random. You'll say approximately normal stated. That's usually the nice one. But for the most part, central limit theorem is what you want to check first. If that doesn't work, I would check one of these other options. If both of those are not happening, then we cannot assume that it's normal. Now, the big difference here for our sample means is our population mean is going to still be the true mean. So we're going to center around mu. Whatever the original claim is, whatever the thought of mean is, that's usually where we're going to center our data. Remember, when we are calculating probabilities, we want to live in their world. We want to see, based on what they are telling me, what's my probability of getting this sample. So we always center around what the problem is telling us. And standard deviation is calculated differently because you are going to get a standard deviation for the population for one individual sample, one group, one individual item. And with sample means, you're taking the average of multiple items. So what we have to do in order to get the true standard deviation for our distribution is take the standard deviation they're giving us and divide it by the square root of the sample size. And these two formulas are also on your formula chart, so they're not something that you have to remember. But I will say, for the most part, this is one of the common mistakes on an exam. Make sure that you're not just using the standard deviation you are given, that you are actually calculating the standard deviation for the distribution that you're interested in. And again, sigma is population standard deviation, n is sample size, mu is the population mean. Okay, so a lot of it's similar to what we did on Friday of last week. So we're just going to go ahead and go on to some example problems. For example 1, it is known that each individual Halloween treat given out has about 120 calories with a standard deviation of 50 calories. To examine this, you collect a random sample of 40 Halloween treats. So notice that they've given us a mean and a standard deviation for an individual Halloween treat. So this is going to tell me that when I'm going to build my distribution for a sample of 40, I need to make sure I'm calculating my standard deviation based on the fact that I have a sample of 40 and not just an individual treat. So first, let's go ahead and check our assumptions and conditions. The first one we will have is random. And it tells us we did a random sample, so I'm going to say random sample stated. Second condition is going to be our 10% condition, and I'm just going to go straight into the statement that I generally write for these types of questions. I'm going to say assume at least 400 Halloween treats in the population. Now, this is the same thing as saying Halloween treats greater than or equal to 10 times 40 is equal to 400. Just remember, you want it to be at least 10% of your population. At least less than 10% of your population. Sorry. I generally write the sentence because it's one of those things where it's the same thing written over and over again, and that tends to be what is easiest to remember. And the third thing is going to be our normality. Now, I always write normality just because there's multiple ways you can check this. And again, I try to build these patterns into your head so that you can remember it when you have to answer it on an AP question. So when I look at my sample size, it's 40. So I know that the central limit theorem is going to apply. And again, this is one of those nitpicky things the AP exam has. You have to actually state n is equal to 40, which is greater than or equal to 30. And then we will say that the central limit theorem applies. CLT is perfectly fine. You don't have to write out central limit theorem, but you do have to have this statement indicating that it's going to be approximately normal. It's absolutely necessary that you write this. Otherwise, they'll just say, yeah, 40 is greater than 30. I don't know what that means. They get very picky when it comes to conditions, if you have not learned already. So yes, we'll just say n is large enough that central limit theorem is going to apply. I'm going to give you a little bit of time to write or type. So once all of your assumptions and conditions are met, you can go on to calculate means, calculate standard deviations, and figure out some probabilities for different situations. So let's go ahead and look at our mean. For calculating the mean of the sampling distribution, remember that it's going to be the mu of the sample mean is going to be equal to the mu of the population, the mean of the population. So for our case, the claim was that the mean is about 120 calories. So I'm going to say it's about 120. And if this is the true mean of the population, it does not matter that I'm taking more than one individual treat in my sample. That mean and those sampling distribution pieces that I build around the center should distribute evenly on either side of 120. So that's why when I'm doing mean, I don't have to do anything with sample size. Standard deviation is a little bit different. I'm going to have to take the standard deviation of the individual item and divide it by the square root of sample size. So I end up with 50 divided by the square root of 40. Plug that into your calculator and you should get approximately 7.9057. Now remember that standard deviation represents how typically off your value is compared to the mean. So within that one standard deviation plus and minus, you should catch about 68% of your samples. Then we go out to 95, then we go out to 99.7. So this is just how off are our values typically. So now that we know mean and standard deviation, we're going to calculate the probability that the sample average is less than 100 calories. So I'm going to go ahead and draw out what this distribution could look like if I can find it. There we go. So remember, we're going to center at 120, and we're trying to find the average is less than 100 calories. So I want this area to the left of 100. I always suggest an image, a graph, a sketch, just so that you can see what area am I actually shading. Once you're not drawing pictures, you tend to flip things a little bit more easily. So drawing usually helps. So I'm trying to find the probability that my sample average, X bar, is less than 100. So what I'm going to do today is I'm going to, when we did proportions, we did it with our calculator only. I'm going to bring it back to z-scores because you will need that as we move into Unit 6. So I'm going to show you another way to approach this problem, especially if it's an FRQ question, because they do require you stating your z-score value. So what I do want to say is I'm trying to find z is less than some number. So remember, the formula for z-scores is z equals x minus mean over standard deviation. In this case, our x is x bar. Remember, this is going to be replaced depending on the context of the problem. Are you doing means? Are you doing proportions? That's going to change, but generally it's just going to be your value of interest. So I'm going to plug in what I know so far. So I know that I'm interested in 100 calories. I know my mean is 120, and I know my standard deviation for this problem is 7.9057. So with this, I'm going to go ahead and calculate what this z-score value would be. And it should be about negative 2.5298. I just plugged this fraction into my calculator. Now you can calculate z-scores separately, just as z equals your equation, a number. Sometimes you can do that, sometimes I will do that, but generally I like to include it in my probabilities, so I'm kind of moving linearly towards my answer. Now, here is a point where you can stop and you can use the table. I know some of us like using the table, and that's perfectly fine. You can also use your calculator to get a probability of this area, of this shaded region. So I went ahead and plugged it into my calculator. And remember, when you're using your calculator, you have to state your calculator input and define all of the variables that you've been asked. So our lower bound would be negative infinity, and we represent that by negative 1e99. and our upper bound was negative 2.5298, our z-score. And when you have z-scores, the nice thing about it is you don't have to change mean and standard deviation. You just leave it as 0 and 1. Remember, everything has been centered to 0, and now our standard deviations are represented by, wow, this is large. I was trying to open my calculator. Our standard deviations are represented by 1 outputs, plus and minus 3. So once I plug this into my calculator, I'm not going to go through these steps again because we did this in proportions. You're just going second vars number 2. I get approximately 0.0057. So remember, normal CDF, second vars, second option. Negative 1 E99 is how we represent negative infinity. So the probability that the sample average is less than 100 calories is 0.57. So what I'm going to do is write a little summary statement for this probability. Probability that the sample average calorie count for 40 Halloween treats is below 100 calories is approximately 0.57%. Some things you want to make sure you include whenever you are summarizing your sentence, your probability. You do want to call it a probability. You don't want to say there is a, because we don't know for sure that our estimation is the value someone will get every single time, or the probability that they'll get it every single time. Sample average, you do want to indicate that you're doing means, and you do want to indicate your sample size, because that does change the value that you get for your probability, because it's used to calculate standard deviation. So you do want to say, I did this based on collecting samples of 40 Halloween treats. And again, always include your percentage. Very, very important. Okay, let's go ahead. And remember, I will post all of these notes. If you miss something while I'm kind of moving along, I'll post them at the end of the day for you to access on our summary doc. So let's go ahead and look at example, if it's going to show up too. The weight of a bag of potato chips is supposed to have a mean of 20.4 ounces with a standard deviation of 1.24 ounces. Again, mean and standard deviation is based on one potato chip bag. The product is declared underweight if it weighs less than 18 ounces, which is stated on the bag. With an SRS of a single bag, find the probability that the product is underweight. Assume that the distribution is approximately normal. So one thing I want to compare before we get into these problems, for part A, we're going to do our calculation based on one bag. And for part B, we're going to do our calculation based on a sample of 34 bags, just so that we can see the difference between doing something for one and doing something for multiple. So let's go ahead and get started. So I'm going to go ahead and check conditions. First thing is we took an SRS of our sample. So I just said SRS is stated because I'm going through and checking conditions. Again, that's something you will always do if you are trying to find probabilities, because we have to check that it's normal and that standard deviation is something that's valid and that our random sample has been taken. For my second condition, it's going to be the 10% condition. We're going to assume at least 10 potato chip bags are in the population because our sample is only 1, N is currently 1. And for normality, this one's pretty nice because it says approximately normal stated. If it did not have this line, I would not be able to assume it's approximately normal because it will not meet central limit theorem, and I don't have any data and I don't have a graph to look at to see a normal distribution. So that's why it has to be there. Otherwise, we're not able to really calculate a probability. So let's go ahead and find the probability that the product is underweight. So for this one, I didn't draw a picture, so I'm just going to go straight into my probability statement, notice that I don't have an X bar here because I don't have a sample mean. I just have one individual potato chip bag. So probability that X is less than 18, I'm going to, again, go the z-score route compared to what we did with our calculator. So I have the probability that z is less than 18 minus 20.4 is the mean of the population. And I went ahead and calculated standard deviation within my z-score calculation. Perfectly fine. I will say most of the time they don't require that you state out mean is this, standard deviation is this. They can look at your z-score calculation and say, okay, they're calculating it correctly. And that's fine with them. So this is something I also do to save a little bit of time. And with square root of 1, because our sample size is 1, which gives me probability that z is less than negative 1.9355. And again, you have the option of going table or calculator. I went calculator in this instance. Second vars number 2. My lower bound was negative infinity because I want everything less than 18 to negative 1.9355. Mean of 0, standard deviation of 1, because we're dealing with the z-score. So my probability, after I plugged that all into my calculator, that x is less than 18 is approximately 0.0265. So a small summary of what that actually means. The probability that a single bag of potato chips is underweight, which is below 18 ounces, is approximately 2.65% chance. So this was just based on one bag of potato chips. Now we're going to go ahead and calculate it for our sample of 34 bags of potato chips. So let's go ahead and look at part B. With a SRS of 34 bags, find the probability that the product is underweight. So I'm again going to run through the conditions because just because it worked for one bag doesn't necessarily indicate that it's going to work for anything else. So you will have to check conditions again. It is stated as an SRS, so we're going to assume the random condition is met. We can assume that there are at least 340 potato chip bags in the population. And normality, in this instance, central limit theorem is going to apply because 34 is greater than our 30 cutoff value. So we can say CLT applies, therefore it is approximately normal. So for our first problem, it was stated that it was normal. Second problem, central limit theorem worked. And when all of our conditions are met, we are able to go in and actually calculate our probability. And this is going to work very similar to what we did with part A. Only difference is I'm going to calculate the probability that X bar is less than 18. And I'm going to change how my standard deviation looks. Everything else is the same. The difference is I'm taking the square root of 34 as my second denominator, not the square root of 1. And this is one of those instances where if you are calculating this using the main home screen of your calculator, I really suggest using that alpha y equals option to enter in fractions. It helps keep your information organized because technically you have a second denominator and you may not remember your whole keep change flip rule from algebra. So those fraction bars help you immensely. Once I plug all of this into my calculator, I'm going to get the probability that z is less than negative 11.2857. Now, before we move on and we get the magic number that we need for probability, I want you to take note of how large this, or how small this z-score value is. Remember that in 3 standard deviations, I'm capturing about 99.7% of all possible samples. So for me to go out 11 standard deviations, I'm really not expecting to get anything or the probability to be 0. Because if I'm catching 99.7 within 3 standard deviations, there's going to be nothing left over by the time I get out to 11. So when I plug this into my calculator, normal CDF, negative infinity to negative 11.2857, mean of 0, standard deviation of 1, the probability of me getting this sample mean is approximately 0, and your calculator is going to output 0. I would always double check. I would always verify that you've typed in everything correctly. But when you have a z-score this large, remember z-scores are representative of standard deviations. If you have one this big, you are generally not going to have a probability. There's not going to be a chance it occurs because most of it is caught within 3. So when you get outside of 3, your probabilities dwindle to 0 or 0.00004 or something very, very, very tiny. So we will still say a little summary about this. The probability that the sample mean weight of 34 potato chip bags is below 18 ounces is approximately 0%. So the chance of me taking a sample of 34 bags and their average being less than 18 ounces is 0%. I have a 0% chance of that happening. That's when we can lead into inference testing, where I say, I've built a normal model based on what their claim is, and the chance of me getting the sample is 0. So for me to get it is really, really suspicious. It's really, really leading me to think that maybe an original claim is not true. So this is our probability for a sample of 34. I'm going to head into, unless I have any big objections, which I'm not seeing any in the chat, the next problem. Yes, yes, okay. No objections. For example 3, we are going to assume that the duration of human pregnancies is approximately normal. That's nice because I'm not going to have to check normality, with a mean of 266 days and a standard deviation of 16 days. Remember, this is just a mean and standard deviation for one individual. At least how many days should the longest 25% of pregnancies last? Notice that they did not give me a value. They gave me a percent. They gave me a probability. They gave me an area. So this is going to flip things a little bit, and this is kind of just review of things you've learned before. I want to see, if I were to sketch this out, what is the sample mean that is the cutoff for the longest 25% of pregnancies? So I have an area, I want a value. So we're going to go ahead and use a feature in our calculator to do so. Something that you have to remember is our formula for z-score. Z is equal to, in this case, a sample mean minus mu over standard deviation. Now, if I've been given an area and I want a value, in your calculator, you're going to not use normal CDF. Let's open this up. Second vars, you're going to do inverse norm. Now, for problems like this, you don't necessarily have to check conditions because we're not going through and calculating probabilities. Instead, we are just getting values based on the fact that it's already telling us it's a normal distribution. So for things like this, you do not have to check every single condition. So I'm going to go to inverse norm, and notice it's going to ask you area, mean, and standard deviation. Well, if I go back to my question, I want to find area of 25%. Well, in your calculator, and if you are using a older model of the TI, you will not have the option of left, center, right. So I always treat these problems like your calculator is going to, and it's from left to right. That is the area you want to enter. So if I'm interested in the top 25%, I'm not going to enter in 0.25. Instead, I'm going to enter in 0.75 because I want the area from left to the right of that value. So again, you have to state your calculator input, label what you are writing, output what you get from your calculator. And I am doing this in terms of calculating a z-score. So I'm leaving my mean as 0, standard deviation as 1. If this was a multiple choice question, I would say it's perfectly fine to go in and change mean to be 266, standard deviation will be 16. But for the sake of the problem and of looking ahead to FRQs, we're going to do it the z-score route. So now that I know my z-score value, I'm just going to plug that into this original formula. 0.6745 is equal to x bar minus 266 over 16. And then I'm going to get that x bar is approximately 276.792, which means that approximately let's see if I can find where my clicking is. There it goes. Approximately the longest 25% of pregnancies last at least 276.792 days. I always try to throw in approximately because we are estimating and we are not going to say for certain that this value is the value for every single possible sample ever. It's just our estimation based on a given mean and a given standard deviation. And for example 4, we're going to do something very, very similar to what we did for example 3. It's exactly the same thing. We're just using a different situation. Assume that the rainfall in Ithaca, New York is approximately normal with a mean of 35.4 inches, standard deviation of 4.2 inches. At most, how much rain falls in the driest 20% of all years? So this time I'm interested on the opposite end of things. If I were to do, let's find where my drawing is. There it is. If I wanted the driest 20%, so my cutoff for the lowest 20% of samples. So I'm going to go through. I just like to give you a reminder of what the formula is. I'm going to plug this into my calculator. And what's nice about this is because I'm interested in the lower 20%, I can just enter in my area directly as 0.2. Don't have to take the opposite of anything. Just going to leave it as 0.2. And I get negative 0.8416. Plug that into the formula. Do a little bit of algebra, multiply by 4.2, add 35.4, and I should get 31.8653. So approximately the driest 20% of all years in Ithaca, New York has at most 31.8653 inches of rain. Now, with this, I will post your practice assignment to Google Classroom. It's going to be another PDF from me just because I'm not super in love with what my lab has to offer for this unit. And you will have time in class tomorrow to work on it.